तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Hello everybody. So we have been seeing over the past 9 lectures on basic electronics, learning by doing. We have, in the previous lecture, we saw about Zener voltage regulator, how Zener diode can be used as a voltage regulating device. We also saw some practical applications of a regulating circuit. Then we saw the different types by which we can construct a regulated power supply, and we also saw how easily we can make use of 3-terminal integrated circuit regulators, IC regulators like 7805 or 7815, as the case may be, where the last 2 digits corresponds to the voltage that you want to obtain as the output after regulation. For example, 7806 means 6 volts positive regulator. 7912 means negative voltage regulator with a 12 volts output. So we also saw how these 3-terminal regulators, IC regulators, can be used very quickly for constructing regulated power supply with fixed output voltage. Now let us continue with our discussion and move on to the next topic, which is basically about transistors. So far we have seen the passive devices like resistors, capacitors, inductances, diodes, and then different types of diode like light emitting diode, photodiode, and Zener diode, etc. So now we move on to the next very important device in electronics, which is basically the transistor. The transistor is a very important device, as I said, because it is one of the active devices. I have already explained to you in the earlier lectures what an active device is. An active device is something which can amplify or magnify the input signal, as against the normal passive devices, which are like the diodes and the resistors and things like that. The resistors and the capacitors can only attenuate a signal, can only diminish a signal applied with reference to the output, whereas a transistor can also amplify. So transistor is one of the very important active devices that we will be learning about. We will briefly see some of the features of transistors, about its construction and about its characteristics during this time. You know, the diode is basically a 2-terminal device. It has got two terminals across. One is corresponding to the p-type semiconductor, the other is the n-type. You form a junction with the p and n-type semiconductors. That p-n junction diode is actually having 2 terminals. Now the next question is, what will happen if we go on to one more layer, one more level? Instead of p and n, I go for p, n and p, or n, p and n. So you can see I can have a 3-terminal device as it is shown on the screen. You can have a n, p and n, 3 regions of semiconductor, or it can also be p, n, p. So these are 2 different types of transistors that you come across, and terminals, there are 3 terminals, you can see they are designated there. One is called the emitter, the middle one is called the base, and the last one is called the collector. So you can have 2 different types of transistors. One is called NPN transistor, the other is called PNP transistor, where the N means it is a semiconducting area which is having majority of electrons, N type charge carriers, namely electrons. So we also know that in this N region there will always be a minority carriers, which are basically holes which exist because of the normal temperature at which we operate. Only at absolute 0 there won't be any holes. So normal temperatures, you know, due to intrinsic conductivity, there will be a small quantity of holes present in the N doped semiconductor in the first region, and therefore N is called the majority carriers and the holes here are called the minority carriers for obvious reasons, because the holes will be very, very small in number compared to the N. Similarly, in the P type region, the majority carriers are holes, and in the last N region the majority carriers are electrons. So you have NPN transistor, and you can also have, as I already mentioned to you, PNP transistor, where the P here means majority holes, and then in the N region majority electrons, and here majority holes. So you can have 2 different types of transistors. They have very similar behavior for most of the applications, but there are slight variations which we will perhaps discuss at some appropriate time when we come across those differences. So for the present we can assume that in principle, in terms of the operational details, both NPN and PNP transistors are almost of the same type, identical nature. Now we should also remember that the names given to them have got some specific meaning. For example, emitter means it is capable of emitting. So you can have emitter means this N region will emit electrons into the base region, therefore it is called emitter. And the base region is the region over which this emission will take place and the transport of charge carriers will take place, and therefore this is called the base. And the last region, which is called the collector, is the one which will collect all or accumulate all the electrons or the charge carriers that are flowing through the transistor, therefore it is called the collector. You can immediately recall a very similar situation with reference to vacuum tube triodes. These transistors are solid state devices which are replacing the well known olden days vacuum tube triodes. In the vacuum tube triodes, as the name itself suggests to you, it has got 3 electrodes, triode, and the 3 electrodes are called filament or cathode, a control grid, and a plate. The filament or the cathode is the one which is used for emitting electron, thermionic electrons, I briefly mentioned to you in the historical background, and then the control grid is the one which is controlling the flow of electrons, and the plate is the one which is normally held positive, which collects all the electrons. And therefore you can see that there is a correspondence between a triode, a vacuum tube triode, which has got 3 terminals, and a transistor which is equivalent in performance in terms of amplification action and all that, and it also has got 3 terminals, and they are called emitter, base, collector. Just as the filament heats up and then emits electrons, here the emitter emits electrons or holes and into the base region, and the base region is the region where the flow of electrons are controlled, and therefore it is like the control grid of a vacuum tube triode, and the plate is the one which is normally held positive to attract all the electrons or collect all the electrons, and the equivalent here is the emitter, is a collector which collects all the electrons when they flow. So you can see in terms of the names that you are the functions, you find there are a lot of similarities between a vacuum tube triode and a 3-terminal transistor that we discuss. Now I have shown you the details of the 3 layers NPN and PNP, and I have also shown you on the screen the circuit symbol of the NPN and the PNP transistor. So you can see the base, collector, emitter, yeah, and all the things, and then there is an arrow which actually distinguishes the two, right, the emitter, the NPN transistor and the PNP transistor. Right. Now the transistors appear, I have already shown when I discussed about the various components. I showed you some of the transistors, and they come in different sizes and in different encapsulation. I have shown you some of the pictures here for recapitulation. Again, you find there is a small semi-cylindrical package which is called the plastic encapsulated transistor. This is one type. It is called a TO92 package in computer parlance, in the electronics parlance. TO means transistor outline, 92 is a part number. So transistor outline 92 package corresponds to this type of a package, where you can see the collector, the base and the emitter are shown by the symbol C, B and E, and the actual construction inside will be something like that. This is a metal electrode, these are other two electrodes, and this is the region where you have actually the semiconductor PNP or NPN as the case may be, and the leads are taken and connected to the external electrodes, so that we can use this in any given circuit in whatever manner we want, by soldering or by connecting to a breadboard or something like that. So these are the connecting leads. Otherwise, this transistor region itself is a very small region, as you can see. Within the very small region you have all the three layers, the N layer, the P layer and the N layer as the case may be, and therefore this obviously brings down the size of the transistor. I mentioned to you that in comparison to vacuum tube triode, the transistor will perform almost the same function of amplification or whatever, but the greatest advantage that you get here is that it is going to be very small, and therefore there is miniaturization which comes along with this. Your transistor receiver or whatever electronic circuit that you build can become very small, and you know there are other benefits like very low voltage operation and things like that, which I already mentioned to you earlier. And if you look at the bottom view, that means you are looking from the bottom side, and you can see the E, B, C terminals, which are actually pins coming out of this surface, and these are the emitter base collector terminals, which will have to be used in any given circuit. There are other circuit packages that I have shown here. One is a very popular TO5. TO5 means transistor outline number 5 or transistor outline number 18. They differ in the size. For example, they look similar. For example, there is a metal can. Okay, there is a metal can, and you have a small region where the NPN or PNP semiconductor region is held, and the leads are taken from them and connected to 3 external leads which are on the header, as they are called. This part is called the header, and over the header you put a metal can and seal it hermetically, so that there is the environmental conditions like moisture and things like that will not affect the transistor operation inside. So the bottom view is shown at the last picture on the right. You can see that there is the emitter, the base and the collector. So this is an identifying tab, it is called TAB, identifying tab, and from the tab you go along the clockwise direction to identify the various pins. For example, the first pin after the tab is the emitter, and the next one in clockwise direction is base, and the next one is a collector. So this tab is the one which is used in identifying the different pins in this type of metal can, and you should always remember it is a bottom view of the can that we should consider when we want to identify the pins. Whereas in the case of ICs, later on you would find you should always look from the top view. Here we have to look at the bottom view and then identify the pins. Now this is again one more transistor package which is called the TO3 package, transistor outline 3 package, and there is also a plastic package, TO221 package. Two different packages are shown here, and this is usually a very big transistor which was also shown to you earlier in one of the earlier lectures, and this has got big metal part, and the big metal part forms the part of the collector. Then you have two other pins which will come over here like it is shown in this other diagram, and they are the emitter and the base. So the emitter and base are only shown as two independent pins, and the collector is formed by the metal can itself, the total metal can. That obviously shows that it has got a different purpose to serve apart from being a transistor which is capable of amplifying or whatever. This will handle much larger power. So this is used for power applications. This is called a power transistor 3055. There are several such transistors which you might perhaps you will come across, and this is a power transistor, and this is of a bigger package, and that is shown on the side view on the right. This plastic package, which is called T transistor outline 221 package, is also similar to the 3-terminal regulator that we saw in the previous lecture. You have here 3 terminals, and this is also meant for larger power than the normal small can or plastic package or TO5 or TO18. So here again you have 3 terminals, they correspond to the emitter base collector, and they can be used for high power applications. Okay, so what is a transistor? Transistor is an active device, I already mentioned to you, and it is a very important device used in several applications, in integrated circuits, in microprocessors, in all different types of electronic circuits. There are 2 types of transistors that we know of, basically in terms of the behavior. They both will do maybe the similar functions like amplification, but they are different in their working principles. For example, one is called the BJT, which is bipolar junction transistor. So it is a bipolar junction transistor, that is what we are going to discuss today. But there is another type which is called field effect transistor, FET, field effect transistor. BJT means bipolar junction transistor. So the bipolar means that the transistor operation will depend on 2 different types of charge carriers. I already mentioned to you. One is the hole, the other is called the electron. So in a BJT there will be contributions to current due to both bipolar, that means both electrons and holes. Whereas in an FET, basically it is the field effect transistor is a unipolar device. In that there are only one type of charge carriers, either a N channel or a P channel you will use, and therefore you will use either a N type transistor, conduction will be due to N type electrons, or the P type holes. So that is a first major difference between these two, but we will discuss little more details of the field effect transistor later on. But the BJT is what we are now discussing about. This is basically a current controlled device, and the field effect transistor is a voltage controlled device. So there are several relative characteristics which will come into the game when you really want to construct very specific types of circuits. We will discuss them. Both of them they have the 3-layer device, PNP or NP, and in this case even in the field effect transistor you will have the source, gate and drain, 3 terminals. Okay. They have 3 terminals that I already mentioned to you in the BJT: emitter, base and collector. Hereafter we will only discuss more about the bipolar junction transistor. And you can see that it has got 2 junctions. Let me go back and show it to you the earlier figure. You can see there is one junction here between N and P, that is called the junction between emitter and the base. So it is called the emitter base junction, and the other one is between the collector and the base, and so this junction is called the collector base junction, and this one is called the emitter base junction. In all the 2 transistors you have 2 different types of junctions. One is the emitter base junction, the other is called the collector base junction. Okay, I already mentioned to you that it is very similar to the triode. That is what I have mentioned here in this slide. Now let me just go ahead and show it to you. A typical transistor with the 3 layers. There is a N layer here, and there is a P layer which is shown in a different shade here at the center, and you have a collector region. Now if you want to operate the transistor, you have to have 2 different voltage sources. You have to apply a voltage source between the emitter and the base, and you have to apply another voltage source between the base and the collector. So you require 2 bias circuit. One is called the emitter base bias, the other is called the collector base bias or collector whatever. So it depends on how you use, in what configuration and all that. So in the basic configuration, we can say there is a power supply between the emitter and base, and it is called VBE here in this picture, and it's a very small voltage source, just about 1 or 2 volts. Whereas if you go to the collector base junction or the collector base side, you find you have a much bigger power supply, and this is very important. So you require larger voltage source on the collector base side, and you require a smaller voltage source on the base emitter junction, and they can be connected in different ways, as you can see. For example, I have connected this is a NPN transistor, I have taken the example, and the N is connected to the negative here, and the P region, base region, is connected to the positive with reference to the power supply. So this, you know what it means. In the diode we know when the P is connected to the positive, N is connected to the negative, the diode is said to be forward biased. So what happens to a forward biased diode? This also we have discussed in the previous lectures. When you forward bias a diode, you have a low resistance for the across the junction, so it becomes a easy current flow path. But when you reverse bias, that means when I connect the N type to the negative positive and the P type to the negative, then you find the resistance of the junction increases, and therefore it is not useful. In this case, what we have done is we have connected the N type to negative, P type to positive. That means the emitter base junction will be forward biased. This is a very important point. Now if you look at the collector base junction, you find the N type of the collector is connected to the positive of the large power supply, and the P type of the base is connected to the negative of the power supply, and therefore the base emitter, the collector base junction will be reverse biased, as you can immediately recognize. So this becomes a high resistance path. The emitter base junction is a low resistance path, the collector base junction is a high resistance path. So this is the configuration of all the various possibilities that you think of. For example, I can forward bias this, I can reverse bias the base emitter junction and reverse bias the collector. So several possibilities are there. The most important and useful way of connecting a transistor is to make use of the emitter base junction as a forward biased junction and make use of the collector base junction as a reverse biased junction. Why is it very useful? Then you can see now, when I connect this in this forward biased way, then the electrons, the junction will become the width of the junction will become very small, because when I forward bias, the width of the junction will become small, and the electrons will start crossing over to the base region or the P region, and similarly the holes from the P region will cross over to the N region. So they will both exchange. When that happens, I am trying to say that electrons are emitted into the base region. We are not worried about the holes, we are more worried about the electrons. The electrons are emitted in the base region. That is what is happening when I apply a low voltage forward bias condition for the emitter base junction. Now these electrons, when they come to the base region, two things can happen. One of the very important things that can happen is these are electrons, and there are abundant of holes in the P region or the base region. Therefore some of the electrons can get trapped by the holes, thereby you know what is going to happen. We will use both the electron and the hole in the bargain. So if that happens, this is bad for the device, because we have lost an electron and the hole. But you can also have another condition, that is the electrons in the base region, as you all know, is a minority carriers, because base in this case is a P type semiconductor. In that the electrons are pushed from the emitter, and these electrons are minority carriers on the P region or the base region, and therefore these electrons will be finding it very easy to cross over to the collector region, because for them there is no potential well or barrier here between the collector base junction. The potential barrier in this junction is only for the P holes on the left side and the electrons on the right side, whereas what we have now in the base is abundant of electrons which have come from the emitter, and therefore they will find that there is actually a valley for them. Therefore they will slide down and go into the collector region. The other way to look at it is this large power supply will provide a very large field across the junction, so that these electrons will be attracted towards or collected by the collector region, positive region of the collector, and therefore you would find most of the electrons which are emitted by the emitter into the base will find themselves happily on the collector side, but there will be finite number of electrons which will find corresponding holes and they will be lost, but this loss will correspond to a small current in the base region which is called the base current. So the electrons moving in this direction will correspond to a current in the opposite direction. You know, conventional current is opposite to the direction of electron flow, and therefore this corresponds to a small base current. So if you look at this circuit on the base side, base emitter side, you will find there will be a very small current flowing through the base, there will be a large current flowing through the emitter, because there is a the electrons, large number of electrons are emitted in the base. That means there will be a current in the opposite direction, because conventional current is opposite to electron flow. So there will be a large current flow here, there is a finite small current into the base, and there will be a large current flowing into the emitter collector again, because all the electrons coming into the base are collected, most of them are collected by the collector, and therefore there will be electron flow into this. Almost 90% of all the electrons emitted in the base will come to the collector, therefore there will be a large flow of electrons here which corresponds to a current in the opposite direction. So IE will be basically equivalent to IC plus IB. Some electrons are collected by the collector, some electrons find the way through the holes and back into the base region, and therefore that corresponds to a small IB. So IB plus IC will be equal to IE. This is a very important relationship we should always remember. Now what is the basic action of the transistor? What is the transistor action here? The transistor means, what do you mean by the word transistor? It is transfer resistor. You can see the electrons are pushed through two different regions having two different resistances. The first region is a low resistance region, and the next region, which is the collector base region, is a high resistance region with a reverse bias junction. Therefore I am able to push this almost the same amount of electrons through a low resistance junction into a region which again automatically passes on to a high resistance region. Therefore you find I am able to push a large current through a large resistance on the collector base junction, and that corresponds to product of large current into large resistance is large voltage. So you can immediately see there is a voltage amplification because of the transfer resistance. This is a low resistance region, this is a high resistance region, I am pushing a current through that. For pushing the current I require a very small voltage. Therefore there is an amplification, there is an advantage, mechanical advantage type of thing. You send a very small, with small voltage you are able to push large number of electrons, and these electrons are automatically collected by the collector, and therefore through a high resistance region, therefore you get a current, the voltage gain, there is a voltage amplification. There is no current gain, the current actually is falling. IE is slightly less than IC because some IB is lost, but still because this almost the same IE is flowing through the base emitter junction and the collector emitter junction, you find the voltage developed in the collector region will be larger, and therefore there is a amplification associated with this. So this is the basic action of a transistor. Now there are a lot of important voltages and currents which come into the game. This is called common base circuit. Common base circuit, because the base you find is common to the input side or the output side. In any amplifier you have two input and two output side, but in the transistor we have only three leads. Therefore one lead will have to be used common to both the input and the output. So if I use the base region as the common as it is in this diagram, you find this becomes a common base amplifier or whatever. So this is a common base, you have the emitter here, you have the collector here. In this case IE is equal to IC plus IB. From the directions also you can see, from KCL also you can see, and then if you look at the voltages, there is a voltage between the base and the emitter which is called VEB, voltage between the emitter bias base, and there is also a voltage which is VCB, which is the voltage between the collector and the base. The applied voltage will almost be equal to this. Now let us see how we can use it in some simple application. Now what I have done is I have used a battery which is VBB on the left side between the emitter and base. This is a PNP transistor, and on the right side I have used a large voltage source VCC between the collector and the base region. Now what is going to happen? I connect a mic here, microphone, and on this side I connect a loudspeaker. Now when I speak into the mic, what is going to happen? It is going to generate some electrical pulses, voltages, fluctuating AC voltage due to the vibration of the diaphragm and things like that. So there is a small AC voltage which will be generated, and what will be the effect of this AC voltage? The effect of this AC voltage is to modify the constant base VBB voltage that I have connected between the base and the emitter by a small variation. So this will correspond to a small variation of a similar type in the emitter current. So the amount of electrons emitted into the base will also fluctuate in the similar fashion as the current generated here. But because this is a forward bias thing, large number of electrons will be fluctuating in this direction. All these electrons will also flow through this, and they will flow through this loudspeaker, and therefore you would find the current through the loudspeaker can be much larger than the current generated by the microphone. So you will get a much larger amplification here. So this is a very simple scheme to understand the basic amplification, voltage amplification of a transistor. So I have shown the two structures of the PNP and NPN once again, where I have shown you the forward biasing and the reverse biasing corresponding to the PNP transistor and the NP transistor. This we have already seen in detail. Now I want to use this transistor in a slightly different way for understanding the current gain also. You just saw how you get a voltage gain in the case of a transistor. Now if by changing the configuration you can also get current gain. We already saw when I have in the case of a transistor action, when we discussed, we said there is going to be a very small base current. So now if I use the base as the input current device, input terminal, if I use the base as the input terminal and the emitter as the common terminal and use the collector as the output terminal, then you can see for making very small currents here you require very small voltages only at the input. But this voltage, this current, when it comes to the collector, you would find it will be very large component, and therefore there is a current gain which is called in this case beta. The IC by IB is called beta, or the current gain of the transistor. The current gain IC by IE is called the alpha in the case of a common base amplifier. So here we are using a common emitter configuration. So here there is a very small base current and you get a very large collector current. This can be very easily shown. For example, if I have a lamp here and connect the same 6 volts to the transistor, this is a transistor, NPN transistor, you have a lamp here, you have another lamp here in the base, and you have a resistor in series, and that is connected to the base, and the emitter is grounded. So now what is going to happen? If I wire this circuit, you would find this lamp with this resistance, for example some 100 ohms or 200 ohms, there is going to be a very small current flowing through this, right? There will be a very small current flowing through this. This voltage is nothing but the forward biased junction of the base emitter, and you know for a silicon the forward bias junction voltage is around 0.65 or 0.7 volts. So we almost know all the time that this voltage VBE for a silicon transistor is going to be about 0.7 volts. So if this is about 6 volts, that 6 volts minus 0.7 is the voltage available for passing the current through the lamp and the resistor. If you neglect the resistance of the lamp, this will be a considerable current only decided by the R. So the lamp will normally glow very lightly, very dimly, because of this presence of this resistance. But this is only the base current. This base current will introduce a large collector current in this circuit, and therefore you would find the lamp in the collector will be very bright. This will become, there will be a large current flowing between the 6 volts and through the collector and the emitter, and therefore the lamp will be glowing brightly, but this current will flow only as long as there is this current provided by the base circuit. If I remove this resistor by disconnecting the circuit, you would find this lamp also will go off, because for making this transistor work you have to have a forward biasing of the base emitter junction, and therefore you have to connect a lamp or a resistor or whatever with a power supply to make a finite voltage appear across the base emitter junction, which is corresponding to about 0.65 or so. So only when this lamp will glow. Now if I increase the value of the resistor, you would find this lamp will not show very significant change in intensity, but when I increase its resistance enormously, for example 10,000 ohms from 100 ohms, if I put 10,000 ohms, this lamp will not even glow, because the current through the circuit will become very small, but this current you will still see some glow here, even though it will be somewhat less, there will be a glow here. That means there is a amplification which comes into the game, and this amplification is called the beta of the common emitter configuration. Now this can be very nicely shown, demonstrated, I will show you also later on, that by removing this R, if I introduce another resistor which is called LDR. What do you mean by LDR? LDR is light dependent resistor. It is a cadmium sulfide semiconductor device. So when you shine light, its resistance is very small. If you cut off light, its resistance becomes very high. The small and the high can be of the order of some kilo ohms and mega ohms. So the variation in this resistance can be brought about by light falling on it. Here I removed the 100 ohm and introduced 10k, 100k, etc. manually, whereas here that can be done by the amount of light falling on it. So if I put a LDR here, if I close the LDR completely, the resistance of the LDR will become very large, and therefore there is very little current, and so the lamp will not even glow. But when I remove my hand, more light falls on this. You would find the resistance of the LDR will become very small, so there will be a large current flowing into the base, and therefore the large current flowing into the lamp, and the lamp will be glowing down brightly. Therefore you can see it can be used as a photo device, optical detector, light detector, or whatever. So several application circuits can be constructed with this basic principle of current amplification in the case of a transistor. So this is what I would demonstrate to you little later maybe. And then there is another aspect which I wanted to talk to you, that is, if I have a gain of beta for one transistor, then if I use combination of transistors, 2 transistors for example, then you might perhaps be able to enhance the amplification factor still further. Here what we do is, this one well known configuration which is called Darlington configuration, after the name of the person who designed this. Here what we do is, take one transistor, connect the emitter of the transistor into the base of the next transistor, and use the emitter of the next transistor as the regular emitter of a overall transistor, and the base of the first transistor is the base of the combination, and the 2 collectors are connected together, as you can see, and this becomes the collector. So you have now formed a new transistor with 1 base, 1 collector, and 1 emitter, but internally you have got 2 transistors combined in the as shown in the figure. When this happens, this is called the Darlington configuration. What is the advantage of this Darlington configuration? A very small base current, you know, will provide a large emitter current in the common emitter configuration. So this large emitter current now becomes the base current of the next transistor. So because there is a large amplification already, this will again be amplified by the current gain of the next transistor, and therefore the emitter current of the overall transistor will be very large. If beta 1 is the gain, current gain of the first transistor T1, and beta 2 is the current gain of the next transistor T2, then you find the overall current gain of the transistor will be beta 1 into beta 2, beta 1 product beta 2. So if this is about 100, you can see if they are almost of the same value, 100 each, then you would find 10,000 will be the current gain of this transistor. So you have enormously improved the current gain of the transistor by using two transistors in combination by a combination which is called Darlington pair. This is called the Darlington pair transistor, and this can be used in several applications. Now what I want to show you is the current gain of this transistor is so large that if I now connect between these two terminals at the base for providing a forward bias, I have to connect some resistor or something here. But this resistor, previously I used some lamp and LDR and all that. Instead, if I now put my hand, connect my hand, two hands, one hand here and one hand here, you would find I will be including my body resistance, right? Every body has got a body resistance. It depends on the skin temperature and things like the dampness of the skin and all that. So it will normally be very, very high, of the order of several megohms. But even if it is very high, of the order of megohms, you would find 6 volts by megohm will be in very small currents of the order of microamperes or less. Even that current, because you have a very large current gain, which is 10,000 or beta 1 product beta 2, you would find that will be able to provide enough current here and make the lamp glow. This is another demonstration which I would like to show it to you. So let me just quickly show it to you, these two demonstrations, and I will come back to the transistor characteristics, and then we will discuss about that. So I have shown here the circuit which is wired here, and you can immediately see it is a very familiar circuit which I already shown just a few minutes ago. You have a transistor T1, the emitter is grounded, and in the collector I have connected the lamp, and in the base I have put a resistor and a lamp. This lamp I have not connected, okay. This lamp is not connected here. This resistor I right now have LDR. Right now I will remove it and put some small value of resistor, for example some 100 ohms or so. So I have connected a 100 ohm resistor here in the base circuit, and I have connected a lamp in the collector. This is the 6 volts lamp, and the emitter is grounded by using the black wire, exactly similar to this circuit. I hope you are able to see this. Now if I connect the power supply lines to the collector end and the other end negative to the negative end, you would find the bulb is glowing because there is a base current and that is amplified, and so you get a very bright glow. Now I remove this resistor here and I connect a much larger resistor, maybe about 1 kilo ohm or so. Let us see what happens. So when I connect a 1 kilo ohm resistor, I am sure you can see the brightness of this lamp has come down compared to the previous case, because now I put 1 kilo ohm here. This current now is much less than what it was before, because it is 10 times larger, this resistor. Now I want to put still larger resistor, that means 10 kilo ohm. Let us see what happens. Now I put a 10 kilo ohm resistor here, and you can see the lamp is barely glowing. There is not much current at all, even though there is a very faint glow here which perhaps you cannot see, and therefore you find as I keep on increasing the resistor here, the current decreases, and hence the corresponding current on the collector side also is decreasing. Now this manual variation of the different resistors is brought about by using the light dependent resistor. You can see by changing the amount of light, there is enough light here which makes the resistance of the LDR, which is shown here, very, very small, and therefore you get yes glow here. Now if I close it with some cardboard, you can see immediately the resistance increases, therefore the lamp is no more glowing. When I take it out, the lamp is glowing. Now the lamp is not glowing. Now if I have another 6 volts lamp connected, which I can bring it closer, you find the intensity of the bulb is much higher. Now this bulb is glowing with much higher intensity. If I close it, it is gone. If I take it out, it is glowing. So you can see this is what I mentioned, that we can make use of very simple circuit with a transistor as a current amplifier and an LDR to make a optically operated lamp. Now you can also extend this concept. Instead of a light dependent resistor, here if I use a thermistor. What is a thermistor? A temperature dependent resistor. So if I remove this and introduce a temperature dependent resistor, you would find when I heat it with a matchstick or a candle, the resistance will come down, the lamp will glow brightly, and when I cool it, you will find the lamp will go off. So you can see I can make use of this simple circuit for different applications, to detect temperature, to detect light, or to detect magnetic field. We have a magnetoresistance and what have you. Different types of sensor resistors, resistive sensors can be used here and in a very simple circuit, and you can learn about the application of the circuit. Now let me quickly go on to the next demonstration which I want to show you, which is by using the two transistors. These are what are known as SL100 power transistor of the TO5 package that I already mentioned to you, and I have two transistors connected in the Darlington pair configuration, and in the collector I have a lamp connected of this Darlington pair. The emitter is at the bottom, so that is connected to the negative of the battery power supply. The positive of the battery is connected to the collector circuit, and now I have two leads coming from them, which are the ones where normally I will connect a resistor. Instead of connecting a resistor, I am going to touch with my hands. Now when I touch them with my hands, my body resistance come into the game, into the circuit, and therefore you find a very small current flows through the base, but because there is a Darlington pair, there is enormous amplification which is corresponding to beta 1 into beta 2, and therefore the lamp is glowing. When I remove my hand, it goes off. When I touch, again it comes on. When I remove, it goes. So you can see it is only because of my touching that you get the current there, and therefore you can immediately see the Darlington combination can help in amplification, in current amplification by a large extent, and that is what is shown here in the circuit. The Darlington connection is shown with the lamp. This is exactly the circuit that is put here. So you find in a very simple scheme, a basic transistor can be used for amplification purposes, and very simple application circuits can be built using this transistor circuit. Now let me also show a very simple demonstration of the same thing over on a breadboard. You can do it yourself by simulation here. So you have the two Darlington transistors connected in Darlington configuration. So I switch on the power supply and I apply the voltage, and if I touch, you can see there is a hand coming and touching here, immediately the lamp is glowing. These two Darlington provide a very large current gain, therefore the lamp is glowing, and when I remove my hand, the lamp goes off. So when I again touch, the lamp comes on very brightly. When I remove, it goes off. This is exactly what we saw in the circuit just now demonstrated. So you do have here a very similar circuit which is also shown to you earlier. Now what about the characteristics of the diode? The transistor, as I already mentioned to you, has got three terminals. That means there is an input side and an output side. The input side, what you have is a base emitter junction, and so if I want to study the input characteristics, then you know what it is going to be. It is just a diode. Base emitter junction is just a diode. Therefore when I have a input characteristics which is shown on the screen, you can see you have a VBE here, which is the base emitter voltage, and you have an IB, the base current, and you can see it is nothing but a normal diode characteristics. Beyond 0.4, 0.5, the current starts increasing enormously and there is very little change in the voltage. So this is a normal diode behavior that you know of. If it is a silicon transistor, this cut-in voltage will be around 0.65 or so, and if it is a germanium transistor, it will be 0.1 or 0.2. But I can, while I am doing this variation at the base emitter junction, this variation, this is what is called VBE, I can have some fixed value of resistors between the collector and the emitter. So, if I have a 5 volts power supply between the VCE, then this will be the graph I will get, and if I replace it with a much larger voltage, then you would find you will get a slightly different curve, but overall it is just similar to a forward biased diode. So, there is not much of an interest on the input characteristics, except that it behaves more like a transistor or a diode. But if you come to the output characteristics, then you find you have a VCC, the VCE, the collector emitter voltage is on the x axis, and you have the IC or the collector current in the y axis. This is called the common emitter configuration, which is the most useful configuration in transistor application. So, this is for a NPN transistor in common emitter mode or the CE mode. Here you find, I will again go to a smaller simpler picture. You have the VCE and you have IC. What you do is you maintain a constant base current of about 10 microamperes by adjusting your emitter base voltage VBB. You adjust the emitter base voltage, maintain a base current of about 10 microamperes or so, and now what you do, you increase the VCC, the voltage between the collector and emitter, by changing the VCC power supply, and you would find initially the collector current will slowly increase linearly, and beyond some point it will remain constant irrespective of the voltage that you increase on the collector side. So, you would find the graph will look almost flat beyond some 2 volts or 1.5 volts, and beyond some 30-40 volts, depends on the given transistor, it may even break down, and then you would get very large current flowing through the device. Then it will become perhaps spoilt, because a large current flowing will produce large heat, and that may damage the transistor. So, we should not go into this region, but you would find the graph looks with a small linear region and then almost a flat constant collector current. That is what you get for a given 10 microampere. If you go for different base currents, you would find higher base current. For example, 20 microampere if I take, you would find this saturation comes at a later stage. That is what is shown in the graph that is shown here on the screen. You find this is for one current IB is equal to 10 microampere, this is for the second current IB is equal to 20 microamperes, and this for 30 microampere. So, as you keep on increasing the current, you would find the graph will go according to what is shown here. Now, initially you find this is a linear region that you have here, okay, and then you have a flat region, and then you have a breakdown region, but you should never go into this region, and that is dictated by what is the maximum power rating of the transistor. Every transistor can be operated with a maximum power to deliver a maximum power, to dissipate a maximum power. So, you should never exceed that power rating, and so that is given by V into I, the maximum VCC or VCE and the maximum IC. IC max and VCE max product gives you the power rating, and that is basically a rectangular hyperbola, and therefore it will come something like this as shown in the picture. So, that is the limit beyond which you should never operate your transistor, you should never go beyond this limit. So, you would find this is the region in which you should make your transistor to work for you for different applications, and this is the output characteristics of a transistor. In this case it is an NPN transistor with common emitter configuration. Now, we will so this is actually the basis under which you will design your circuit. So, it is like a map for a given device. The characteristics is such an essential part of the design that you have to have a clear understanding of the transistor characteristics to really make use of them. And I mentioned to you that it is like a map, and if you want the transistor to operate in a particular way, you have to fix the operating point of the transistor circuit in somewhere in this region. It is like saying in a map you are here. Only when you say in a map, given map, you are here, then the whole map becomes meaningful to us. Otherwise we cannot understand what the map says. There will be mountains, there will be trees, there will be everything else, but you can never understand on which direction they are unless somebody tells you you are here. The moment the map tells you with an arrow that you are here, you are able to understand the whole map. So if I go along the east, there will be a tree. If I go along the west, I will get a mountain or something like that. So it is very important that you should provide a bias to a transistor before you can operate it. That means what? You must make sure that transistor is operating in forward bias condition with reference to the base emitter junction and reverse bias condition with reference to collector base junction to make it into an amplifier, for example. So such ideas are very important in the design. So we will see how the output characteristics can be used to fix a operating point, and we will discuss about how the transistor can be biased. That is a technical term, how the transistor can be biased to make it to operate at a very specific point along its characteristics, and how the amplifier can be used for different applications. The transistor can be used for different applications. We will see all these in the next lecture most probably, and then we will not discuss all the different configurations possible. We will try to identify very important concepts with reference to the applications of transistor in different circuits, and we will focus only on essential configurations and discuss their features in some detail, and we will also perhaps see how the characteristics can be obtained, and wherever possible I will also try to show you the exact circuit working, and then the readings can be seen and verified. So I think I will stop here. In the next lecture we will talk about transistor biasing and how transistor amplifiers can be made use of using the simple common emitter configuration. Thank you.